let me tell you that is for me a great honor and a great pleasure to be here, and I want to thank to the organizers for this invitation. So this session is about smart grids, but we are going to focus our attention on the topic of the microgrids because, as you will see, microgrids are in fact, or at least we think so, they will be the building block of the smart grid, the grid of the future. So, I'm going to talk about the use of microgrids and distributed energy resources for black start and islanding operation. And I will start by describing the main concept behind the microgrid. So what is a microgrid? Well, it can be a low voltage distribution system with a small modular generation that can provide electricity and or heat to local loads. And it has also a local communication infrastructure and has an hierarchical management and control system that is, as it is represented in this picture. So the different microgrids, you can see them connected at a low voltage network. And there is a microgrid central controller, an MGCC, that is housed at the medium voltage, low voltage substation. And then there are controllers at the level of the loads and the level of the microsources. And this microgrid that, as you will see in the next presentations, can be a little bit larger. It can also include medium voltage or even high voltage networks and be related with the grid of an island, a big island. But this is a kind of a cell, the elementary cell of the development of this concept. And this cell, it allows the operation in two modes. What we call the normal interconnected mode, and the normal interconnected mode means that so the microgrid is interconnected with the upstream network. And then there is an emergency mode that is related with the possibility of operating this microgrid completely separated from the upstream network, so the islanding operation. It can be intentional or not, as we will see. It can be even a forced islanding, and we can even foresee the possibility of having the microgrids participating in black start, local black start. Now I'm expanding the concept. So we can have a medium voltage network made of several microgrids that are connected among each other through the medium voltage network. And then, of course, this means a larger geographical dimension with a large number of active players that can be loads, some loads that can even be controllable, and also dispersed generation units. I'm talking about PV plants or wind generators. And this control structure can have an architecture such as the one that is described here. So we can assume that we have at the level at the high voltage, medium voltage substation a kind of intermediate control infrastructure that is called controlled autonomous management controller. And this establish communication links with the microgrid central controllers that are housed at the level of the microgrid, and that, of course, the microgrid communicates with the controllers of the microsources and the loads, I mean. And of course, at the medium voltage network, there are also communications with the DG units, with the online tap changing transformers, with the capacitors, and so on. And so, very important, and I want you to understand this, that the development of a smart grid and the development of a microgrid as a building block of the smart grid, it requires a communication infrastructure. This is fundamental. And so smart meters, they can be used as nodes for communication. And for last mile communication protocols, we can have power line carrier, radio frequency wireless mesh networks. Well, there are different ways to communicate. In order to understand the way how we have addressed this topic, I would like to call you about, to give you an overview on the microgrid operation control and control issues. So, very important, and I believe you already understood that microgrids are inverter-dominated grids. So, because so the PV panels, the wind generators, they will be small wind generators, microturbines, batteries when they exist, all of them, they will be connected to the network via inverters. So this will be an inverter-dominated grid. And this will be also a grid with a very low global inertia. And this is also a key issue. And when there are some synchronous units, if they exist, because they can even not exist at all, but in some situations, there are also microsources with slow response times, as I will show you. And so we may have load tracking problems related with the slow response of microturbines, fuel cells, and this brings problems that need to be addressed properly via batteries, because batteries are the element that will keep energy and will serve as a buffer in terms of energy in order to balance the operation of the grid. So it is extremely important that in order, when we want to move to an islanding operation, that we are capable to compensate for the changes in load or for the changes in generation, and for that we need energy storage devices. So we can have in islanding operation, we can have an intentional islanding when it is related with maintenance issues, or we can have a forced islanding because there's a default upstream in the grid, and then suddenly the microgrid becomes islanded. And in this way, this requires that locally we have devices that will be capable to respond to frequency changes and should be able to keep the balance locally. And so we have to adopt control strategies that combine frequency control solutions, mainly related with the control of the storage devices, and also in some cases we also consider the possibility of having load shedding. And also the microgrid can participate in black start. So I suppose that most of all of us, we know that when a black start occurs, typically a black start is solved via a restoration plan that is a restoration plan that utilities go through making it, solving the problem from top down. So they start energizing the lines from top down, and it may take a lot of time, hours, or in some cases even more than one day, to fully recover a system in these situations. Well, what I want to bring you here is a new approach. That is, since we have several sources distributed over the distribution network, and also if we have batteries that are capable to keep the balance in the operation of the system. So why not to make a local black start and solve the problem of the restoration of the system following a blackout, not from top down, but from bottom up. And in this way, create islands and afterwards synchronize these islands. So, and that's what we have done. And for that, we have developed first a set of, a library of Microsoft dynamic models. We have performed lots of simulations, but we have also developed a laboratorial infrastructure, and this is something that the next speaker is going to present. And as you will see, this is the approach that we adopted to bring credibility to what we are developing. So, in fact, as I said, we developed a library of dynamic models for different microsources, so fuel cells, microturbines, wind generators, PV generators, storage devices, flywheels, batteries, all the devices that can be connected at the level of the microgrid. They have been developed, and then it was necessary to start defining control approaches in terms of for the management of the power electronic interfaces. And for that, we have conceived the following set of solutions. So what we call the PQ inverter control, that is designed for grid, mainly for grid connected operation. So the inverter is controlled to meet an active and reactive power set point. This is the way how it works, and it follows the frequency of the grid. In addition, this inverter is also obviously capable to keep the voltage on the DC link. Afterwards, it is necessary to consider another type of inverter. This is an extremely important type of inverter, what we call the voltage source inverter or grid forming inverter, that is really the one that is designed for standard operation, in a lone operation. And in this case, the inverter is capable of controlling voltage and controlling frequency, and is usually connected to storage devices, flywheels, batteries, and so on. And the control approach that we used is this one. So we have for voltage and frequency a droop control mode approach. We can then classify the microsources in different types regarding control. So we can have the grid forming units that, as I said, are the so-called VSIs, related with the connection of storage devices to the grid. And they will keep voltage and they will keep frequency, in fact, so they will be really responsible for the balance, the power balance in the grid. Then there are also what we call grids supporting units that can be microturbines or solid oxide fuel cells that are capable to be to respond, but they have a slow response, and they can be used to try to balance the operation of the grid in certain situations, especially in the ones that are related with the intentional islanding. And then we have the so-called grid parallel units that are the ones that have no big control capabilities, and there are, for instance, PV and micro wind generators. They just produce and they inject what they produce into the grid. Then we have to think about the way how all these inverters are going to be operated and controlled. And for that, we started by defining what we called a single master control strategy. In a single master control strategy, the microgrid central controller, that is in fact the brain of the microgrid, is going to send set points, PQ set points, to some of the PQ inverters, and it's also going to send droop settings to the voltage source inverters when necessary. So this is the situation where there is a kind of a chief of orchestra, and the chief of orchestra is in fact the VSI, the only single VSI that is keeping frequency on the grid. But it is possible to have a kind of a multi-master operation, which is the normal operation that exists in a network when there are several voltage source inverters connected to the grid. And so in this case, so we need to operate the network taking into account that there are all these inverters with each one with its droop, and so they will share the burden of keeping the frequency in the network. And so this is the so-called primary frequency control, and so it is up to the voltage source inverter to, in fact, to keep the frequency on the basis of a droop frequency control mode, and the voltage source inverter is responding proportionally to the frequency deviations. And in some situations, extreme situations, it is also possible to adopt load shedding strategies that use controllable and interruptible loads. And in this way, they are used to try to keep and to bring a fast response in order to solve imbalanced situations on the grid. Obviously, they are used for really emergency situations, and they are used to aid frequency restoration following some islanding situations. But as it happens on the large interconnected system, it's not enough to have only inverters that respond to primary frequency controls. It is necessary to have a secondary loop of control for frequency, that is a secondary frequency control. Otherwise, if we don't do it, for instance, since the inverters of the batteries are responding proportionally to the deviation of frequency, they would keep on injecting power in the grid while the frequency would be maintained. So we don't want that. And because of that, it is necessary to bring frequency back to the nominal value, and therefore there is a secondary frequency control based on the proportional integral control approach. This is a typical solution. Now I'm going to show you some results we obtained from dynamic simulations on a microgrid test system. And so this is the test system we used, where we have several microturbines, we have PV panels, we have fuel cells, and there is also a main storage device there. And this test system has been modeled from the point of view of MATLAB, and in a MATLAB platform, so this is the image that you get when you pass from the test system in a single line diagram to the simulation platform with all the models, where each one of those boxes corresponds to one of the units, one of the elements that is going to play and to have a responsibility in the operation of the microgrids, especially when operated in islanding manner. Now, let's look at some of the simulations we did. For instance, microgrid intentional islanding. So this is a situation where, as I already said, a situation where the distribution system operator needs to make maintenance actions from the medium voltage side of the grid. And it is not mandatory that when they do these maintenances, they will just cut the supply to all the consumers that are downstream. Because in this case, since these microgrids, they have the capability to produce by themselves and to operate in an islanding manner. So it is possible to, in the first moments, to try to bring the active power outputs of the different devices to the values that will bring the power flow in the transformer of the medium voltage low voltage substation to almost zero value. And then at, for instance, in this case, 120 seconds, we perform the islanding. So, and in this case, since everything has been balanced before, there was almost no problem at all in this islanding. But it may happen that the network may be forced to face forced islandings. And in this case, the type of responses that we may have are here described, where you can see the moment where the islanding took place, immediately frequency dropped a lot. There are here different frequency control groups and frequency control solutions. And you can see the moment that is exactly at about 10 seconds, so frequency dropped, and because there was an imbalance on the grid, and then we can see the way how the other variables, the other power outputs of the other devices are responding. We can also see the way how the secondary frequency control is afterwards going to respond. And here you can see that in the previous slide, there was here an offset in frequency because there was no secondary frequency control, while now the secondary frequency control has been taking control of the system and is bringing back frequency to the nominal value. And this obviously is made at the cost of the control of some of the devices that have some controllability in terms of producing power and injecting it into the grid. Also, very important is, I would like to call your attention for the injected power from the voltage source inverter. The voltage source inverter that is connected to the battery. At the first moments of the imbalance, it's really up to this voltage source inverter and up to the battery to make an injection of power into the grid in order to keep the balance. Otherwise, we will lose the equilibrium in the operation of the microgrid. And okay, we can also see what are the effects of load shedding. So not only primary, secondary frequency control, but also load shedding. And the benefits are obviously the ones that result from the fact that we have not so deep frequency deviations when we use load shedding in these situations. We can also get an idea of the operation and of the response of the microgrid in terms of load following during islanding operation. And so in this case, we can see frequency changing in time according to so the way how the output of PV plants, the way how the load has changed during the operation of the system, and in this way we can see if the system is capable to respond and to operate in these conditions. So, microgrid operation issues. How do we achieve a seamless transition in order to ensure the microgrid survival? What are the key issues? First of all, is the energy available on the storage device enough for the seamless transition? So it's not only to have batteries, it's also to have enough energy on the storage devices in order to keep the operation of the microgrid balanced within a certain time. How much load can be shedded if necessary? And so these are questions that are very much related with the frequency stability and the ability to restore the balance between local generation and local loads in the moments that follow an islanding. Now I'm going to talk, as I promised on the very beginning of my presentation, I'm going to talk about the use of microgrids for service restoration. So these first generation units, they have technically matured enough to offer ancillary services, and in this case, black start. And black start in any system is no more than a sequence of events that is controlled by a set of rules. So these rules, they are embedded, they can be embedded in the microgrid central controller software that I recall you that the microgrid central controller is in fact the brain of the operation of the microgrid. So we are going to embed this set of rules on the microgrid central controller. And so we can define these rules, and these rules, they include building the low voltage network. Building the low voltage network means energizing the network, connecting the microsources, connecting the controllable loads, controlling voltage and frequency, and finally, when it is possible to operate and to keep this operation for enough time in order for the upstream network to have power and to have voltage from the upstream side, to make the synchronization with the medium voltage grid. So it is also extremely important, in order to have success in the black start of a microgrid, to have local generation that has capability to have a local black start. And as in any big transmission system, this is necessary. So it is necessary to have at least one unit. It can be a battery, it can be a microturbine, but so it is necessary to launch local generation, and in order, namely, to energize the network. So this is necessary for that. Then we have an hierarchical control that is going to send set points to the load controllers, to the microsource controllers, and so the microgrid has an ability for also to deal with the disconnection after system collapse. This is extremely important because when the system fully collapses, what is required is that all loads should be disconnected. Otherwise, if they keep connected to the grid, in the first moment when we start to energizing the network, immediately the frequency drops because there's a big load that is going to demand load that is from this local generation unit, and it's not capable to do it. So it is necessary that these loads should be disconnected from the grid, as well as microsources. And also the disconnection of the distribution transformer. Otherwise, if we keep the distribution transformer on, when the network is energized, we have the phenomena of energizing the transformer. And the energization of the transformer requires reactive power, and so this is a transient that we want to avoid. And obviously, it is necessary to periodically record the microgrid status in terms of its operation. Then, in terms of sequence of actions, we are going to adopt a multi-master operation in the initial stages of this procedure. So, disconnection of all loads and sectionalization of the microgrid so that the microsources may feed its own loads, creating small islands inside the microgrid. Then, afterwards, start energizing the low voltage cables, synchronize with other microsources, connect controllable loads, and connect non-controllable microsources. So this is the sequence. And at the end, we can change the microgrid control scheme to a single master operation, and at the very end, to make the reconnection to the main grid. I have here now an animation just to show you how this may happen. So let's suppose that we have a fault upstream in the medium voltage network, and so the system collapsed completely. So is a black start. So what is necessary to be done afterwards is, as I said, to disconnect all the microturbines, all the loads, everything should be disconnected from the grid. Then it is possible to start some units that have local black start capabilities, like the microturbines or even the fuel cells. Then the storage device also. And afterwards, we can start feeding local loads by these microturbines, these fuel cells, creating local islands. Afterwards, we can start energizing the grid. And then it is possible to connect more loads, and at the very end, to connect more PV generation, more wind generation, non-controllable generation. And in this way, we can arrive to a situation where the island is back in operation and is capable to operate in islanding manner. So let's see now some results of some simulations we performed with this test system, where there was microturbines, PV panels, storage devices, and so we were capable to deal with fast transients, but not only the fast transients, the main transients. For the fast transients, we have not used MATLAB, we used EMTP-RV, and for the long-term dynamics, it was the MATLAB simulating platform that I just presented to you. And this is the result. This is the result, and you can see the frequency, the way our frequency has evolved. And here you see that at the beginning there are 3 frequencies. Why 3 frequencies? Because they correspond to 3 islands inside the microgrid. And so there are obviously large imbalances at the beginning, and so this brings to large frequency deviations in the system. But we progress. As far as we progress, we start making the synchronization of the islands, and we arrive at a single frequency on the grid. And it is possible also to see the behavior of, for instance, of a load connection, how load connection impacts the frequency, as it is here described. And you can see that following a load connection, obviously frequency dropped. And when a wind generator was connected, frequency increased. PV panels were connected, frequency was increasing again. But then, at the same time, the local primary and secondary frequency controls were taking care of the frequency of the grid, and they were bringing back frequency to the nominal value. And in this case, we have even simulated motor load startups, just to see if the microgrid during the restoration stages it was possible. The microgrid was robust enough to face motor load startups, and it was possible. And we can see also here, so the active power, this I suppose is the active power from the voltage source inverter, and so the battery as a matter of fact, and this is the power from the different microturbines and the way how they were responding. And this is the global impact in terms of frequency from a sequence of restoration actions, and also the impacts in terms of voltage from a sequence of restoration actions. Obviously, there are some transients, but the frequency was kept in a narrow band of operation, that is a reasonable band of operation, obviously at the cost of the presence of a battery capable to inject power and responding fast to the sequence of load connections and PV and wind generator connections. So, in fact, the point that I want to stress is that in order to be successful, the storage device is key in all this operation of the restoration. And I'm about to finish, but I would like just to call your attention that we can we can expand, we can transpose this strategy, this approach when dealing with the medium voltage network. So assuming that it is possible to restore the service at the level of the microgrid, afterwards it is possible to transpose to the level of the medium voltage network an islanding operation of the same, in the same strategy, in the same manner, with the same approach. And so this is the set of steps that should be followed in order to restore the service at the level of the medium voltage network. And I'm just finalizing. These are my main conclusions. And so the key issues for a successful microgrid operation are: first, an adequate sizing of the storage devices coupled with static converters. And I believe that you understood from my presentation that storage is really key for the success of such situation. Because the other devices, I mean PV generators or wind generators, they don't have energy and they don't have the capability to respond fast to these situations unless they are operated in a deloaded manner. But this is a very sophisticated procedure, a very sophisticated approach that is not conceived at the level of a low voltage microgrid. It can be conceived for a big microgrid, but not for this case. Also, it is necessary to think about the possibility of using efficient load shedding mechanisms. And very, very important is the need of a secondary load frequency control. Otherwise, frequency will drift, will not return back to the nominal value, and it is extremely important to have it back to the nominal value. Otherwise, the batteries will keep on injecting power and will exhaust the energy that they have stored. Another message that I would like to leave you is that it is possible to develop these hybrid bottom-up, top-down approaches for black start. This is extremely important because in this way we are capable to reduce the total restoration time following a blackout. And this is something that utilities, system operators are looking more and more. We all know about the extreme events, hurricanes, storms that many times take place and that completely destroy the distribution network infrastructure, and afterwards it takes days, hours and hours to restore service. So it is possible to, in this way, to bring service, to bring power back to the consumers in a more fast manner. And finally, I want you to understand that microgrids are the building block of the smart grid of the future. And so thank you very much for your attention. If you have any questions, we will keep it for the end of the session. I hope that you had, I could give you some good ideas for you to develop some research, and I would like also to tell you that we are happy, we'll be happy to collaborate further with you if you are really interested. Thank you very much.